Hello everybody, welcome to the 4.1 through 4.2 notes. There's two big topics we're going to talk about here. The first one is interpreting the meaning of derivative in context, and then the second one, 4.2, is straight line motion. And so we'll start with interpreting the meaning of the derivative in context. So a lot of the ways that we've been talking about the derivative most recently is that the derivative is the slope of the tangent line. And that is true, that's what it looks like graphically. But if we think about the derivative in the real world, like how does it help us with the real world? If you guys remember, the derivative is the instantaneous rate of change. And so we've used that language, we haven't used it in a little while, but the derivative is the instantaneous rate of change. So if anybody ever asks you to find the instantaneous rate of change, they're asking you to find the derivative. And what that means is it's the rate of change of a function, but it's at a particular point in time. So for example, average rate of change is over an interval of time versus an instantaneous rate of change is happening at an exact moment in time. And so what we're going to learn how to do today is how to interpret a derivative in context, how to explain what it actually means. And so to do this, there are 4 things you must include when you are talking about a derivative in context. And so the first one is you have to talk about the context of the function. Context of function. So for example, if your function is talking about snowfall and how much snow has accumulated on the ground, then if you talk about the derivative in context, you need to talk about snow. The other thing you need to talk about your rate of change. So somewhere you need to say, my rate is. And sometimes you'll say the rate is increasing, sometimes you'll say it's decreasing. So somewhere in your problem, you're going to say, at this moment in time, the rate of change is. Then, because it's an instantaneous rate of change, you also need to talk about the instant this change is occurring. And so the instant is normally the x value that's given to you. But basically, this is your point in time. You have to talk about your point in time. And then finally, because you're talking about a real world situation, you need to use units. And because it is a rate, rates are always going to have a per involved. So I'm going to say there's going to be a per involved always. So for example, miles per hour is a rate of change. Miles per hour. So you're going to need something like that every single time you do one of these problems. And so we're going to look at our first example. The function for this first example, it says a pie is taken out of the oven. The temperature of the pie in degrees Fahrenheit, t minutes after the pie is removed from the oven, is given by the function p of t. And so my function represents the temperature of this pie, and then my input is t in minutes. And so what we're going to do first is we're going to interpret it with just like normal function notation. We're not even going to talk about the derivative at all, but we're first going to talk about what does p of 10 equal to 100 mean in context. Well, what that means is 10 minutes after the pie is taken out of the oven, its temperature is 200 degrees Fahrenheit. So 10 minutes after the pie is taken out of the oven, its temperature is 200 degrees Fahrenheit. So that's normal function notation. But now what does it mean if I do p prime of 10 equals negative 13? So as I write this, I got to make sure I have all 4 things. I need to have my instant, my context, my rate of change, and my unit. So I normally start with my instant. So I'm going to say 10 minutes. I'm going to use the same thing I used in the last line. 10 minutes after the pie is taken out of the oven. So I've included right here, that's my instant. 10 minutes the pie is taken out of the oven. The rate, so this is when the other stuff comes in. Or sorry, I'm going to say the temperature is, so that's a negative number right here. It says p prime of 10 is negative 13, so the derivative is negative 13. So it's going to say the temperature is decreasing at a rate of 13 degrees Fahrenheit per minute. And so that's how you would interpret something in context. I have the instant right there. Here I have my context. The pie is taken out of oven, the temperature. Right here I have my rate. I said decreasing at a rate of 13. And then I also have my units, degrees per minute. And so 10 minutes after the pie is taken out of the oven, the temperature is decreasing at a rate of 13 degrees Fahrenheit per minute. And so that's what the derivative at 10 means. So we'll do one more example like this, and then we'll move on to position, acceleration. Oh, well, we have two more, sorry. And then we'll move on to position, acceleration, and velocity. And so we're actually going to do 3 different statements here. One's the derivative, or one's the original function. The second one is the derivative, and the third one is the double derivative. So this one says Lena drove from New York City to Philadelphia. The function d gives the total distance Lena has driven in miles 2 hours after she left. So let's start with this first one. This is pretty easy. After 2 hours, Lena has driven 125 miles. 125. Oh, sorry. I'm reading last year's. I edited some things. So after 2 hours, Lena has driven 80 miles. So that's what the regular function is. Now let's talk about the derivative. So this says d prime of 2 equals 65 in context. So 2 hours after Lena left, or you could say after 2 hours, doesn't matter. There's like different ways to word all of these. You just have to make sure you have all the parts. 2 hours after Lena left, or I'll say started driving. Again, it doesn't really matter. 2 hours after Lena started driving, she drives at a rate of 65 miles per hour. So there's no like increasing because she's just driving. It's not like like in the last one the temperature could have been increasing or decreasing, but she's just driving now, and so this is just how her like distance is changing with respect to time. So 2 hours after Lena started driving, she drives at a rate of 65 miles per hour. So I have all the things. I have my instant, I have my context, I have my rate of change, and I have my units. But the double derivative is going to be a little trickier. So what this means right here is after 2 hours, the rate at which Lena is driving is, so it's negative, so is decreasing at a rate of 5 miles per hour squared. So I'm gonna write it out. 5 miles per hour squared. So there's 2 things to look out for here. Since it's the double derivative is a rate of a rate, because the original derivative is a rate, so the double derivative is a rate of the rate. So notice that I have rate written twice. And then the other thing that to notice is in my units, I have per hour squared. So I essentially have 5 miles per hour per hour. And so every time you guys go to take another derivative, you add a per to your units. And so we're going to look at an example. I've talked about this before, but the derivative of velocity, or the derivative of position is velocity, and then the derivative of velocity is acceleration. And so technically acceleration is a double derivative. And if you guys think about acceleration, it's always like meters per second, and that's why it's actually just calculus this whole time. So let's go into one more example, and then we will talk about acceleration, position, and velocity. So this says circle the correct interpretation and state why the other answers are incorrect. So the function d gives the day, length, and minutes of the nth day of the year in Juneau, Alaska. What is the best interpretation of the following statement? D prime of 10 equals 3. So just real quick, the inside part is always going to be the same because that's the independent variable. And so this day that it's talking about the 10th day of the year in Juneau, Alaska. And then this just like the day length of that day. So let's just go through. The 4 things I'm looking for again are context, instant, rate, and units. So this first one says on January 10th. So that's a good sign. I have this part. I need that. That's the instant. On January 10th, the day length is increasing at a rate of 3 minutes per day. So we have the context as well because it says the day length, right? And then it's also talking about minutes. We also actually have the rate. It says increasing at a rate. And then we also have minutes per day, and those are the correct units because minutes are the dependent variable and day was the independent variable. And so this actually is the exact correct interpretation. We got it right on the first time. D prime of 10 equaling 3 means on January 10th, the day length is increasing at a rate of 3 minutes per day. But let's go through and talk about why the other ones are not correct. First, this next one says on January 10th, so that does have the instant, that's good. The day is 3 minutes long. Well, there's no rate there, so that can't be a derivative. This actually, if you were to write it here, this is just d of 10 equaling 3. So that's just like what the normal function represents, not the derivative. But the big idea here is there's no rate. If there's no rate, it's not a derivative. The next one says on January 10th, the day length is increasing at a rate of 3 days per minute. This was kind of hard for me to notice, but the units are off. So 3 days per minute, when you write a unit, you always put what the dependent variable stands for first and what the independent variable stands for second. And they did it flip-flop. They did independent and then dependent. So the units are off. And then finally, until January 10th, the day length is increasing at a rate of 3 minutes per day. So the big difference right here is this. Saying until January 10th is making you think of the days between like January 1st and January 10th. And that's an interval, not an instant. So remember, we need an instant. So this is not an instant. Okay, so that is 4.1, and we're going to use the stuff that we learned in 4.1 for the rest of this unit. So none of this is going away. We'll get so much more practice with it, but that is what derivatives mean in context. But now let's go on to one application of derivative, and that is connecting position, velocity, and acceleration. And so we're going to start with position, and position, there are like a lot of different ways that you can use the notation, but some of the popular ones are S of t could stand for position, or P of t. And then the next couple examples, we're actually going to see position being X of t, but it'll always tell you like S of t is position. So don't worry too much about the notation and if you're using the right one or not. But position is always measured in units of length, so like feet, miles, or meters. And so what I've said this before, but the derivative, I'm going to use the S for these next problems, but the derivative of position is velocity. And so velocity actually equals the derivative of position. And so you can get from one to the other that way. And so S prime of t equals V of t. And I'm going to write this in words, but the derivative of position is velocity. And velocity is measured, it says measured in units of length per unit of time. So for example, meters per second. And see that per right there? That's how I know velocity is a rate, okay? Because there's a per. And then finally, acceleration is actually the double derivative of position, which means it's the first derivative of velocity. And so acceleration is derivative of velocity, and it is the double derivative of position. And like I said earlier, if you guys look at these units, so it's measured in units of velocity per unit of time. So it says meters, seconds per second. So there's a per and per. There's like a double per there. This slash right there stands for a per. Okay, so let's go on to like how do we actually use these? There's so many different kinds of problems about these. So there'll be a lot, but that's okay. Okay, so, oh no. I don't like when this happens, but it's okay. They didn't, sometimes the formulas don't copy over, but that is okay. So this says a particle's position along the x-axis in meters is given by, so sorry, let me add the formula in right over here, is given by x of t equaling t cubed plus 16 squared plus 1 for t is greater than or equal to 0. Where t is measured in seconds, find the particle's velocity at t equals 3. So what I want you guys to picture here is there is a x-axis right here, and you have this particle, and it's just moving back and forth on the x-axis. So that's what a straight-lined, this said like straight-lined motion, that's what that means. And so we have this formula right here that represents the position. And so it's t cubed plus 16 squared plus 1, and we want to find the particle's velocity. Well, to do that, all I have to do is find the derivative of this. So the derivative of x of t is 3t squared plus 32t. and then the derivative of 1 is 0, so that goes away. And so this is the derivative of position, which is velocity. And so if I want to therefore find what velocity is, I'm just going to plug in 3 for t. I'll get 3 times 3 squared plus 32 times 3. This ends up being 27. This ends up being 96. And if you add those together, you'll get 123. But then because this is real world situation, I need to add context. So it's 123 meters per second. And so that is the particle's position along the x-axis, or sorry, that is the particle's velocity at time equals 3. So let's do some more problems. This one says a particle moves along the x-axis. The function x of t gives the particle's position at any time. X of t equals 9t squared minus 19. So I'm going to do this, but I want you guys to try this on your own real quick. So I will silently work through this. And that's the answer. If you need more time, pause it. But that's really all you do. It's not too bad. There's going to be a bunch like this. So I'm just going to kind of work through these. You guys can work through them on your own if you don't want to listen to me talk. I actually am going to talk about this one, though, because it has the chain rule. So I lied. Okay, I'm just writing down the equation real quick. Okay, so this one says a particle's position along the x-axis in meters is given by x of t equals 12 sine of pi over 6 t plus 5 for 0 is less than or equal to t, which is less than or equal to 10, where t is measured in seconds. Find the particle's velocity at t equals 6. So the process is still the same. We just have a little bit of a harder derivative to be taking. But the original function, I'm going to rewrite it out here so I can line things up. So if you guys notice, this is a composite function because if you go over here, the outside function is 12 sine, x, or t in this case, since that's the variable we're using, and then the inside function is pi over 6t. And so when I take the derivative of this, I need to take the derivative of the outside function. So the derivative of 12 sine would be 12 cosine, and then I keep the inside function plugged in. And then the derivative of pi over 6t is pi over 6, and then the derivative of 5 is 0. So that's the derivative right there. It really wasn't as bad as I maybe was making it seem. But then now I'm going to plug in 6 to find the velocity. So pi over 6 times pi over 6. These will just cancel each other out. 12 cosine of pi times pi over 6. Cosine of pi is -1. And so when I simplify this, I'm going to get -2 over pi because 12 divided by 6 is 2. So that's how I'm doing that in my head. And that's going to be the answer. And when you guys have pi's, just like don't put it in your calculator. People don't normally do that. And that's going to be meters per second. And so this particle is moving at a velocity of -2 pi meters per second. Okay, we're going to keep going. Example 4. A particle moves along the x-axis. The function x of t gives the particle's motion at any time. So x of t equals 7t minus 3. So this is a different problem. This is the particle's acceleration. And so we'll start by finding the particle's velocity. And this will be actually really nice because the derivative of 7t minus 3 is 7. And so then if we want to find acceleration, we'll take the derivative of that, and the derivative of 7 is 0. And so that right here equals acceleration because the double derivative of velocity is acceleration. And so the answer is 0 meters per second squared. So there's some information we get about an object if we know things about its velocity. So for example, an object is at rest when the velocity equals 0. So it's not moving. An object is moving left or down. So if it's straight lined motion, left. If it's not straight lined motion, we know that it's moving either towards the left or if it's moving down when the derivative of our position, aka our velocity, is less than 0. And so essentially that means that when the velocity is negative, our object is moving left or down. So remember, velocity has a vector to it. And so if it's negative, that doesn't mean it's like slowing down or anything. If it's negative, that means it's moving left or that's moving down. And then likewise, if the derivative of position, aka the velocity is greater than 0, if the vector is positive, that means it's moving either to the right, the object would be, or it's moving up, depending on your situation you're working with. There's some stuff about speed and velocity. So for example, no matter what way you're moving on a highway, north or south, when I ask you what is your speed, it's always a positive number. And that's because speed and velocity, while they're similar, speed is the absolute value of velocity. And so again, velocity is a vector. It tells you what direction an object's moving. Speed is going to just be the absolute value of the velocity. And so it just tells you like how quick you're moving. And so one way that you can tell if an object is speeding up is when the direction of acceleration matches the direction of velocity. So essentially acceleration and velocity are the same side. So if they're both positive or they're both negative, that means that the object you're working with is speeding up. An object is slowing down when the direction of acceleration and velocity are different. And I could go more into depth in this if you guys feel stuck on this, but I do know that this is stuff that you learn in physics. So hopefully this is pretty easy. But if acceleration and velocity are different signs, then the object's slowing down. So if acceleration is positive and velocity is negative, it'll slow down. If acceleration is negative and velocity is positive. Maybe that's the same thing I just said, but you know what I mean. So we're going to do a couple examples real quick, and then we're almost done. So this says a particle moves along the x-axis. The function gives the particle's position at any time that's greater than or equal to 0. And you're going to see that on a lot of these problems because it doesn't really make sense for time to be less than 0. So a lot of times it's going to say like t is greater than or equal to 0. So this is the function, and then we just have a bunch of questions. So it first says, what is the particle's velocity? So let's first find the derivative of velocity, which is 3t squared minus, that's squared. Okay, so 3t squared minus 8t plus 3. So that's the function that represents velocity. Specifically, the velocity at 2 would be 3 times 2 squared minus 8 times 2 minus 3, which equals 12 minus 16 plus 3, which is -1. And then I know that there's no, I didn't put any units on this, but let's just assume it's meters per second. And so the particle's velocity is -1 meters per second. The next one says, what is the particle's acceleration? So to find the acceleration, I just need to take the derivative of velocity. And so the acceleration would be 6t minus 8. So I'm just taking the derivative of 3t squared minus 8t plus 3. And then specifically at 3, it would be 6 times 3 minus 8, which equals 18 minus 8, which is 10 meters per second squared. So because velocity was meters per second, every time you do the acceleration, you add a per. And so that's just the information we're going to need to solve this problem. Well, actually not necessarily, but we'll do it again. So this next question says, what is the direction of the particle's position at t equals 2? And so first, just know that the context is it's moving along the x-axis. So the direction can either be negative or positive. And so you have to, when you answer these questions, you have to give like a little explanation. So the particle is going to be moving to the left, and the reason that is because the velocity at 2 is less than 0. And so make sure to say v of 2 because it's not the velocity as a whole that's less than 0. It's just specifically at 2, it's less than 0. So we know that at 2, the particle would be moving towards the left. And this says at t equals 3, is the particle's speed increasing, decreasing, or neither? And so to answer this question, we would need to know the sign of velocity and the sign of acceleration at 3. And so I know the acceleration at 3. Real quick, I need to find the velocity at 3 to answer this question. So I'll do 3 times 3 squared minus 8 times 3 plus 3. That gives me 3 times 9 minus 24 plus 3. 18 minus 24 plus 3. We'll get there eventually. -6 plus 3 equals negative. Wait. Sorry, wrong math. 3 times 9 is 27. So 27 minus 24 plus 3 equals 6. And so the velocity is 6 meters per second. And so if you guys notice, that means that the object has to be slowing down because, the object is speeding up because the acceleration at 3 is positive and the velocity. So it's going to be increasing, and then you got to give an explanation because velocity at 3 is greater than 0, and acceleration at 3 is greater than 0. So you have to just give like a little explanation like that. Okay, 2 more examples real quick. So this one says a particle is moving along the x-axis. The position of the particle in feet, so we're talking about feet right now, can be measured by x of t equals 1/3 t cubed minus 5/2 t squared plus 4t plus 6 for 0 is greater than or equal to t, which is greater than or equal to 5. So basically we're only concerned about this position, and it's in 5 minutes, where t is measured in time. So just so you know, our units this time is going to be feet per minute and not like meters per second. So when is the particle at rest? Well, if we want to know when the particle is at rest, we would need to know when the velocity equals 0. And so I'm going to start by finding our velocity. So 1/3 times t cubed is going to be 1t squared, because 1/3 times 3 is 1. And then the derivative of negative 5/2 t squared is going to be negative 5t. And then the derivative of 4t is 4. And the derivative of 6 is 0. And so this is the velocity function. But if I want to figure out when it's at rest, I'm going to, if the particle's at rest, the velocity equals 0. So I'm going to set this equal to 0. And then I'm just something really fun, and that is I have to solve for t, and this is a quadratic. And so, wow, you never knew this was going to come back, but what I'm going to have to do this is I'm going to have to factor it, because that's how you solve quadratics. So I'm going to do 0 equals, and then I'm going to look right here, and I'm going to think about, okay, what multiplies to 4 and adds to negative 5, and that would be t minus 4, and then t minus 1, because negative 4 times negative 1 is positive 4, and then negative 4 plus negative 1 is negative 5. And then I will set these both equal to 0. So t minus 4 equals 0, t minus 1 equals 0. And then if I solved, I'd add 4 on both sides, so I get t equals 4. I'd add 1 on both sides, and I get t equals 1. So my answer is t equals 1 and 4. And so at 1 minute and at 4 minutes, our particle will be at rest. Next question is, when is the particle moving towards the left? So this is, we're only concerned about when the particle is moving towards the left between 0 and 5, because our original equation told us that we're only concerned about this particle between 0 and 5 minutes. But specifically, if you think about it, for a particle to move towards the left versus towards the right, before it could switch direction, it would have to stop. And so basically the intervals where it could be changing direction is this, because we know, okay, we're only concerned about 0, and then we're only concerned about 5. It's at rest at 1, and it's at rest at 4. So between those intervals is where there could be a possible change. There couldn't be a possible change at 2 because it doesn't stop. And for something to switch direction, it has to stop even for an instant before it can switch direction. So these are the intervals that we're concerned about where it could possibly be left. And so now what I'm going to do is I'm going to just choose a number in those intervals. I'm going to plug them in. And if the value comes out as positive, that means that the particle is moving towards the right. If that value comes out negative, it means it's going towards the left. And anywhere in this interval, if it's positive on this interval, then every single value between 0 and 1 is going to be positive, because we know that it doesn't switch direction at any point in there, so it could never go to negative. And so I'm just going to choose a value so I'm going to start by choosing a value between 0 and 1 that I could plug in to see if the velocity is negative or positive. And I'm going to choose like the easiest number I can. In this case, there's not really an easy number, so I'm just going to plug in 1/2. And I'm just concerned about whether it's negative or positive. So I'm going to do 1/2 squared minus 5 times 1/2 plus 4. This is going to give me 1/4 minus 5/2 plus 4, which equals, I'm going to convert all of this to decimals real quick, 0.25 minus 1.5 plus 4, which is going to give me 1.75. And so between 0 and 1, this particle is positive, or the velocity is positive, and so it's going to be moving towards the right. Now I have to check this interval between 1 and 4, and I'm going to do 2 because that seems like the next easiest number to plug into that velocity equation. So I'm going to do 2 squared minus 5 times 2 plus 4. I'm going to get 4 minus 10 plus 4. And here's the thing. I actually don't need to go all the way through this, because I know that 4 minus 10 plus 4 is going to come out to be a negative number. So I'm going to just write a negative on that interval, but technically the velocity at 2 is negative 4, right? Yes. last year when I did this. Oh, no. Sorry, it's -2 because -6 plus 4 is -2. Okay, last interval I need to check. So I'm just going to highlight this and I'm going to use a different color. This is, sorry, it's like kind of a different color, but that's negative. And then let's see what's happening in this next section. And so, sorry, I'm going to test out 4.5 because that is a number between 4 and 5. And you can never choose 4 and 5 because that won't tell you like if it's moving left or right. It will just tell you like, oh, it's stopping here. Okay, 4.5 squared minus 5 times 4.5 plus 4. I'm just going to put that in the calculator, and what's going to come out is positive 1.75. And so in that section right there, the velocity is negative, which means our particle is moving towards the right. And so to answer this question, I have to do a little explanation. I'm going to say the particle is moving towards the left between 1 and 2. So that's like interval notation, but between times 1 second and 4 seconds because the velocity is less than 0 on that interval. Okay, one more problem. I know that these are a lot, but they're kind of fun if you really think about it. Example 6, continued. So this is the same problem, but I'm going to rewrite the equation over here at the top. So it was 1/3 t cubed minus 5 halves t squared plus 4t plus 6. 0 is less than or equal to t, which is less than or equal to 5. Okay, so a particle, again, is moving along the x-axis. The position of the particle in feet can be modeled by that equation where t is measured in minutes. At t equals 3 is the particle speeding up or speeding down. So what we need to do to consider this is we need to know what the velocity is at 3, and we need to know what the acceleration is at 3. So we already have our velocity equation, so we'll start with that. We can just pull that from the last problem. The equation was t squared minus 5t plus 4. And so the velocity at 3 is 3 squared minus 5 times 3 plus 4, which is 9 minus 15 plus 4, which equals -2. And so it's going to be -2 feet per second, or sorry, per minute, because that's what this one tells us. And then we need to find the acceleration. So to find the acceleration, I take the derivative of velocity, so 2t minus 5. And then specifically at 3, that's going to be 6 minus 5, which equals -1. So -1 feet per minute squared. And so this one is, that's positive 1. 6 minus 5 is positive 1. So this one is slowing down because acceleration and velocity are different directions. Or you could say because acceleration is positive and velocity is negative. But the big idea is they're going in different, they have different signs, so different directions. And so they're slowing down, they're different signs. Okay, thank you guys for watching all those notes. I know it was a ton, but hopefully you are picking it up.